4.9, antiderivatives. Essential question. How do I use a derivative to find the general or particular function? Okay, let's take a look at what an antiderivative is. Well, we know what a derivative is. Anti would be the opposite of. So we're going in the opposite direction this semester. So if we can find an appropriate antiderivative, we know that when we take its derivative right here, that we will get the function that we originally started with. Let's take a look at this. Find the antiderivative, name it f of x, capital F of x. So here's the function, and we want to find its antiderivative. So I'm going to say its antiderivative is x cubed over 3. Now I'm going to check my work, and the way I'm going to check my work is by taking the derivative of x cubed over 3, and when I do that I get x squared. So I know I have an antiderivative. But it's not unique, because I could have also written this. And when I check my work and I take the derivative of that, I'm going to find I get the same answer. So I really can add any constant here. And when I check my work, again, regardless of what the constant is, the derivative will equal x squared. So find an antiderivative. There's a lot of them. Okay, so we call this antiderivative capital F of x plus c, and c is that constant. So it's this is the most general antiderivative. We know there's specific ones. So let's find the most general antiderivative for the following. So f of x, now I just have to think backwards. So I got to think what function is going to give me the sine of x, and it's going to be negative cosine of x. And when I take that derivative, it'll be sine of x, but the most general, which is what they're asking, I'm going to have to put plus c, meaning that I could have any constant being added. For this particular one, I got to think of what function, when I take its derivative, will be 1 over x, and that'll be natural log of x. Now that's a particular one, so if I put plus c, then I can choose any type of function with a natural log in it and a constant, and its derivative will yield 1 over x. For this particular one, I want to think of how am I going to get this as my derivative. So I know that this is a power rule. I must have been up a power in order to have started that way, and I know that there's no coefficient here, so I must have an x plus 1 plus c. Now again, it's always good to check your work. So the derivative of this antiderivative, x to the n plus 1 over n plus 1 plus c. And remember, the power rule says to bring this down, and it's going to cancel with this denominator, and I'm going to have 1 less, so that's x to the n. Now let's take a look at this. F of x equals the natural log of x plus c, and let's take a look at more details. The derivative of natural log of x is 1 over x, and let's talk about x here. The domain of the natural log has to be positive, so we want to write the absolute value of x right here. And now what happens, now this is going to be forcing the domain to always be positive. So let's take a look at what are we going to call this without the absolute value. If x is greater than 0, then we don't need the absolute value sign. But if x is less than 0, then we want to say the opposite of x. So these are good antiderivatives. Now let's check our work and find the derivative of the natural log of x, and that's going to be 1 over x when x is greater than 0, and we want to find the derivative of natural log of the opposite of x, and that's going to be 1 over opposite of x, and then we got to times it by the chain rule, -1. And so this is going to be 1 over x. So we get the same result regardless of whether we describe the antiderivative this way or this way. Okay, so here's a table of anti-differentiation formulas. And it's all a matter of, if you know your derivatives really well, then you'll be able to find your antiderivatives because they're just going a different direction. So if you see, you know that this, for sine inverse of x, this is the derivative. So if you see this, then its antiderivative will be this. So we're just thinking backwards. Let's take a look at this. And again, we're thinking backwards. And we want to find all functions g such that this is the derivative. So g of x equals, and I'm going to write -4 cosine of x, and I'm going to check my work and think to myself, what's the derivative of cosine of x? It's negative sine of x. Now, this can be rewritten as, I can write it as two fractions, 2x to the 4th minus, and then I take a look at that fraction. I look at this fraction right here, and this will be 1 over root x. So the antiderivative of this will be plus 2x to the 5th over 5. And then this is going to be, remember, think of this as x to the -1/2 power. So this is going to be negative. I'm going to up the power, which is going to be 1/2. And then I'm going to times by 2, so that when I actually take the derivative, I will get this. And then plus c, because I want the most general. And you can, again, check your work by finding the derivative, so you can get back to this. So this is -4, and the derivative of cosine is negative sine of x plus 5 times 2x to the 4th over 5 minus 2, and I'm going to bring this down, power rule, 1/2 x to the -1/2 power, and then the derivative plus c is 0. So you can see I do get back to what I originally had. All right, and differential equations are equations that have derivatives, and to find general solutions is very important in many calculus situations. Let's take a look at antiderivatives graphically. Okay, so here is the derivative, and it tells us something about the function. Well, all the derivatives are positive, so this tells us it's an increasing function. And if you look at f, you can see that it's an increasing function. But also take a look at the second derivative. The second derivative, the derivatives of all of these are going to be positive, which tells me it's concave ups, and we do have this concave up look. And then we have a maximum right here in the derivative, which tells me this is the change in concavity. So from concave up to the steepest slope we have, and then concave down, and you can see this curvature going down. And again, we have a min, which means there's another change in concavity, and we can see that change in concavity is going on right about here, and the change in concavity again is right about here. So the derivative does say a lot about the function. All right, another chance for you to try this problem and turn it off and see if you can accomplish this. And here's the answer. I rewrote the derivative so it looked a little familiar. I found the antiderivative, and then I substituted 0 in for all of these values here, and I got all of these to be 0. Oh, this is 1, so this is going to be 1 plus c. So if I take the 1 to the other side, that's -3. And now I know what c is, and here's my function. Okay, here's a second chance. You're going to have to take an antiderivative twice. Stop the screencast and try. Here's the answer. I'm taking the derivative, first derivative, by taking the antiderivative of this, and I call it c sub 1. Since I'm going to do it twice, I'm going to have a constant again. And then I take the antiderivative again, and then this will be the second constant of the antiderivative c sub 2. I put in my 0 in, and I find that c sub 2 is 4, so I know this is going to be a 4. And then I use this initial condition, put a 1 in for x, 1 in for all these x's, and the output is 1. I get c sub 1 equal to negative 3, and then I'm able to substitute negative 3 in for c sub 1 right here. All right, make a rough sketch of the antiderivative here. Okay, so this tells me something right here. This tells me that the slopes are negative. Then we have a 0. Then the slopes are positive. And then we get a maximum. And then we get a 0. And the slopes are negative, a little bit more negative, and so on. So here's my function. Remember, this is going to be a min. So it doesn't matter where you start. I'm just going to start up here. So I'm going to get a min. And then I'm going to get a maximum, and then I'm going to get a maximum here. So it's going to eventually go like this, and there's going to be a change in concavity, and the change in concavity is about right here. I'm getting a maximum from positive to negative, and as I go down, I'm going to have a change in concavity here. It still can continue down, but then there's a little change in concavity right here. And here's another picture. You can start anywhere. Right now we have, remember that plus C says that this curve can be located high or low, shifting up or down, and this whole curve could have been underneath as well. Rectilinear motion is motion that goes in one direction. A lot of times it's up or down or left and right movement. Let's take a look at how to solve example number 6. We are given an acceleration. We take the antiderivative to find the velocity, use the initial condition, and find c sub 1 is negative 6. This will now give me my velocity expression, which I now take an antiderivative, and then I'm going to have a c sub 2 to differentiate from the c sub 1. I'm going to use my initial condition, and I find that c sub 2 is equal to 1, and now I have a position function here. Stop the screencast and see if you can solve this. One of the first things that I did is I wrote down everything I knew. I knew my initial velocity was 48 feet per second. It was going up, so it's positive. My initial position was 432, and I know that acceleration is due to gravity, which is negative 32 feet per second squared. So I find the antiderivative, and I get this expression. I substitute an initial condition here and find c sub 1 is equal to 48. Once I get my velocity expression, I find the antiderivative with c sub 2, use my initial condition with the position, and get c sub 2 is equal to 432. So now I've answered the first part of the question, which is find its height above the ground t seconds later. Now, when does it reach its maximum height? That's when the velocity is 0. So I set the velocity equal to 0, and I find this happens at 1.5 seconds. The last question, when does it hit the ground? I go back to my position function, set it equal to 0, solve for t. I had to use a calculator, and I got about 6